Ace Podcast.
Hi, this is Adam from Misguided Consultation. You're listening to Vaguely Accurate on the Ace Podcast Network.
Hello everyone, and welcome to a very exciting and very special episode of Vaguely Accurate. As always, I'm your host DK, and today on the show we'll be meeting Helen Czerski. She's a little bit more high profile than what we normally cover on this show, however, I was given the opportunity to interview her for the Cosmic Shambles live tour of Australia, and I couldn't pass that up. Helen is a physicist and oceanographer, and also avid science communicator and broadcaster for the BBC. She graduated from Cambridge University with a natural sciences degree in physics and then awarded her PhD in experimental explosive physics, which is very exciting. And her research interests include optics and acoustics of ocean bubbles, the structure of bubble plumes caused by breaking waves, and the influence of ocean bubbles on the atmosphere. She is also author of Storm in a Teacup. In true Vaguely Accurate style, we go over her research and then we go into a little bit about her science communication endeavours and if she has any philosophies or advice for avid science communicators. Before we start the show today, I'd like to do a brief announcement for a charity organisation I work for. SABRE, or the Staffy and Bully Breed Rescue Organisation, is an entirely voluntary-run, non-for-profit organisation dedicated to improving the image of bully breeds, educating the public about responsible pet ownership, and rehoming and rescuing vulnerable dogs. They operate with no funding and rely on adoption fees and donations generally received from the public to save lives. They're an incredible organisation. I personally volunteer for the charity as a foster owner, and we currently have a beautiful Ridgeback Staffy, 9 months old. He's a delight, so if you hear any barking, that's that guy. I'll put the link in the description, and if you could just check them out to help raise awareness about what they do, that would be truly appreciated. Thank you very much, guys. And lastly, if you enjoy the show, could you please log on to iTunes, subscribe to us, rate and review. It really does help. So thank you very much, guys, and let's get into the show. Thank you very much for coming on the show. For those that don't know, do you mind introducing yourself and telling us a little bit about yourself as well, if that's okay?
I'm Dr. Helen Czerski. I'm a physicist at University College London, and I study the bubbles underneath breaking waves. So the physics part of my job is as a researcher, as a physicist, but I sort of became an oceanographer by the back door because if you work at sea, apparently you get to call yourself an oceanographer. And then I also write and present and do various other things. So I present science documentaries for the BBC. I've just written a book called Storm in a Teacup. And I get out and about being enthusiastic about physics and the rest of science. So that's me.
Do you happen to, when you did your PhD in experimental explosive physics, could you please explain a little bit more about this and what you were looking at?
I got into the topic of my PhD because I was fascinated by the world of things that are very fast and very small, just too fast and too small to see. And the obvious way to get into that world is things like high-speed photography and high-speed diagnostic techniques. And that was the reason I got started. I like building experiments. That's my game, really. And, or that's one of the parts of science I enjoy most, is building novel instruments. And so I chose my PhD because it let me play in that world. And it happened that explosives was what I was looking at, but that wasn't the bit that interested me. I studied condensed matter physics before that, so that was kind of my world. But what I was doing was looking at how solids behave when they're hit, and in particular, there are some common secondary explosives that were actually discovered, a class of explosives that were actually discovered as heart drugs because they've got nitro groups on them, which makes them vasodilators. So they were discovered in the late 1800s as drugs. And then at some point, someone worked out that all those nitro groups actually made them explosive because it meant that the molecule effectively carried the fuel and the oxidizer in the same molecule. And so you don't need any oxygen for these things to burn. they'll go pop in the right situation all by themselves, even if they're underwater or whatever. So these are organic crystals, and at the time, that organic crystals were still a bit of a new, not exactly a new thing, but the idea that they went through phase transitions and the way that they went through phase transitions was quite interesting. And of course, if you're dealing with explosives, some of the solid state phases, the sort of crystalline shapes, are more sensitive than others, which means they're more likely to go pop. So my PhD was all about sort of watching how these crystals behaved and what made them go bang, and also how the shape of the crystals helped focus energy in certain places within the crystal. Because obviously you don't need the whole of an explosive crystal to reach the temperature and pressure to explode. All you need is one tiny bit of it, and then the rest of it just follows. So it was sort of messing about in that world and looking at using the explosive bit, if you like, as an indicator of energy concentration and phase transitions. And so I got to play with, lasers and impact experiments and gas guns and all that kind of thing. So it was a lot of hands-on building experiments.
You got to play with all the nice expensive toys and...
Well, some of them were quite old. I mean, one of the things that's quite nice about experimental science, I think, is that there is a lot of swanky technology, and there's always new things on the shelf, but you get a lot further by thinking about things. So it's obviously sometimes that swanky new diagnostic tool is exactly what you need, but you can go a long, long way just using ingenuity. And so actually I was mostly using kit that was very old, or at least, up to a couple of decades old. But if you're clever, then you can get at the information you need. So it's not just about swanky new toys. The fun bit was about the thinking.
So what brought you or fascinated you into the world of oceanography? Because those two seemingly are quite different worlds, I suppose.
The thing that links them is the size scales and the time scales. So when I finished my PhD, I knew I didn't want to carry on in the world of explosives, and I looked around for a topic that would let me build similar sorts of experiments, but in a slightly more useful context. And bubbles came along. There used to be someone in my lab there'd been a whole section of my lab actually that studied bubbles of a different type, and so I sort of dug around. I finished my PhD and then I spent 6 months doing bits of postdoc work and bits of consultancy and writing up papers and just reading Scientific American and Nature and everything else I could, looking for a field of science that would let me build the kind of experiments that I was interested in. And it's funny because now when I talk about physics, it's very obvious to me that the way I think about it now is that there's this sort of logarithmic size and time plot where you've got very, very small and very, very fast and that becomes the quantum world, and people know there's a frontier in physics there. And you've got very, very long and very, very large, and that gets you to cosmology and theories of the Big Bang and dark matter and all that kind of thing. And those are understood as frontiers in physics. But there is this bit in the middle which is complex, and it's all Newton's laws, the basic laws running those middle size scales and time scales are quite, people learn them at school. But the way that they manifest themselves, because there's all these different things that can matter, that's the interesting bit. You get this messy, complex world. And that's where I work. And at the time, no one really said that. There was nanotechnology and there was astrophysics, and no one had a word for what's in between. And now we're much better at complexity theory and that kind of thing. And we know that there is this third frontier in physics, which is the world of the complex. So I found bubbles, and then that took me to the ocean. And I've never really looked back because I got to work at sea and got to work outdoors. And I'd nearly become a geophysicist several times. It just had physics in it. So I'd found a way into the outdoors world without having to give up on actually doing physics.
That's fantastic. Like working out at sea has its ups and downs, not just inducing to the waves, but did you find just working at sea one of those amazing, utterly breathtaking experiences at times, or did you find it have the ups and downs?
Well, I mean, I'm a very outdoorsy person, so being in an outdoors environment wasn't new to me. The thing I found that was very hard was that what I was used to was building lab experiments incrementally. So you put some things together and you have a fiddle about with it and you make a measurement and then you realize you should have built it slightly differently. So then you build it slightly differently and have another fiddle about, and then you add the next bit on, and you can kind of keep going until you've got your perfect experiment. And then as soon as you've got that, you make some measurements and basically you've got a result. And that's there's a lot of room for sort of you have a lot of control over that situation. The problem with working at sea is that you've got a limited amount of time, you've got very difficult conditions, you've got you've got a ship's captain who, for very good reasons, will only let you put stuff over the side at certain times of day and in certain situations. You've got to share time with everyone else on the ship. You don't know what the weather's going to be doing. So fundamentally, you put this bit of kit in the ocean and then you cross your fingers and it comes back. And you have to make something out of what came back. And sometimes, it's very useful. And sometimes, the weather wasn't quite right, or you didn't get the right combinations of conditions. It's very difficult to do controlled experiments in the ocean because you never get exactly the same situation twice. So I found that was the biggest difference, was that I found it very frustrating that you have to think about how to build your experiment differently in that case. And then you have to work out how to make best, because we're so data poor in oceanography. Even now, I mean, people think that because there's sort of satellites and swanky drones and, underwater vehicles, that all this has solved all these problems, and it hasn't. The ocean is so big and so varied that we never have enough data. And an experimentalist would say, well, you just need to think about it more carefully. But that doesn't, you've still got all the unpredictability of the ocean to deal with. So that was the hardest thing, was sort of switching mentality from something I could control to something that I was kind of following along behind.
Yeah. So one thing that your website actually said is that you look at how bubbles influence the atmosphere. I can see how the application of bubbles and the explosiveness can kind of work together, but how do they influence the atmosphere exactly?
Bubbles are an important component of the interface between the atmosphere and the ocean. So you've got these two massive reservoirs, and you can look at the Earth as a whole, as a sort of engine, if you like, that's got 5 components: the atmosphere, the oceans, biology, rocks, and the ice. And those have all traditionally been studied separately. You've had biologists, and you've had sort of glaciologists, and you've had an atmospheric scientist. But of course, an engine is all about interaction. It's all about how the components work together. And so as we've gone on, we've found that actually understanding how those systems work together is as important as understanding each one individually. So the boundary between the atmosphere and the ocean is important. And when there is breaking waves and storms, it's full of bubbles. And bubbles are really important in helping transfer things between the atmosphere and the ocean. So there are gases, for example. You can take gases of a bubble from a breaking wave is little pockets of the atmosphere carried down into the ocean, and then you increase the chances for gas transfer. And gases can dissolve into bubbles and be carried back up. So they're a two-way vector, if you like, a vehicle. And then also when they rise to the surface and they burst, it's just like when you hold a fizzy drink under your nose, you can feel it spitting tiny particles upwards. So those foam patches on the ocean, as the bubbles burst, they're spitting stuff into the atmosphere, and that changes how clouds form and how light travels through the atmosphere. And so this exchange of gases and particles sounds really trivial. How is a bubble going to affect an atmosphere? But actually, I think the statistic is about 10% of the clouds that we see have at their heart little particles that were spat out of the ocean by bubbles. So it does matter. And it changes how clouds form, and we're still trying to understand that process. So yeah, it's all a big interlinking engine that's full of intertwining tentacles.
It is amazing how much in the field of oceanography is not exactly known, especially, I can't remember the exact step, but like the deep ocean itself, we're only just starting to get the technology that's capable of really collecting high amounts of data at that depth and progressing that field itself.
The problem is that light doesn't travel through water, and sound only travels very selectively, and it doesn't travel very far. If I could invent a ridiculous unphysical device, I would invent a pair of binoculars that let you look down into the ocean the way that you look up into the atmosphere. And just that sort of quirk, which says that both of these types of waves, both light waves and sound waves, are attenuated much more quickly in the water. And especially light just doesn't really go anywhere. That you just don't get light below 200 meters, and the average depth of the ocean is nearly 4 kilometers. So it makes us realize how much we take for granted about the atmosphere, because it just so happens it's transparent, that the electronic transitions which give us the richness of colour in our world are at a window in the atmosphere's absorption, and that's not true in the ocean. So it's opaque. So it is astonishing how little we know about it.
It is. So you feel free to do a plug in for your book in a minute if you want. So you're an author and science communicator, passionate about explaining the science of the everyday. What's caused you to become an advocate of science, and how do you fit it in? As I know, time is an incredible, if not the most valuable resource of any academic, and being a full-time academic as yourself, how do you actually find time to fit in your communication endeavours?
So it's never been conscious in a way. It's just that I'm enthusiastic about what I do, and I like sharing ideas, and it's the ideas that matter and the quality of the way that they're shared. So it was never I never pursued it consciously. I just was enthusiastic about things, and I kept doing it and kept getting asked to do things. So, and then when it comes it's just what matters is the same as what matters in science, which is integrity in ideas. And you have to that they're so valuable and they're so undervalued, I think. There's no point saying something unless you've got something to say. And the world is full of people that open their mouths before they've done any thinking. And I think that's a bad habit. So, and then when it comes to how I fit it in, I've just got more than one job, and I do more than one job. There's no answer to that. I work too hard. I work at university, which is very understanding of the modern world, and they understand that the job description of, basically up until now, the job description of academic is called everything, and there's one job and it's called academic, and there's no sort of there's no layers within that. And no business runs like that. No business expects someone to do the accountancy, the marketing, the product design, the product development, the pitching to investors. No other industry has all of those things required of a single individual, and academia does. And I think as the world becomes, as collaborations become bigger, we have to have a little bit of specialization in there. And so UCL, University College London, is understanding of that. That fine, I do my teaching and my research, but they see me as part of an ecosystem. And not everyone. I have to keep my research going, but not everybody has to do everything. But the system, the ecosystem as a whole, has to do everything. So that, which is much more forward thinking, I think. And there are still universities that don't have that attitude, and they are suffering for it.
So you'd agree with the field of science communication is growing, and we're starting to see more advance in that field with universities, like you said, adopting it. Do you also see industries or like research-based industries adopting the field of science communication more so, and getting a lot more collaboration working on collaboration efforts between universities and academia? Industries, sorry.
The links are growing. The first problem, though, hasn't been fixed, and the first problem is not actually to do with academics talking to the public or with academics talking to industry. The first problem is with academic scientists of any sort talking to each other. The problem in science is that communication is not valued, and it's sort of seen as this throwaway thing. That, of course, you don't have to think. Of course, you can speak your language and you can write sentences, and therefore you can communicate, and that is emphatically not true. And so the problem is that academia doesn't value communication within academia. I've moved fields a few times, even within what we discussed earlier, and it's terrible. The jargon and people's methods of communicating are dreadful, and they're getting better, but they're still dreadful. And so the first battle is to communicate internally and to value that. And the thing is that if you can't communicate clearly, what it really shows is that you're not thinking clearly. It's that hierarchy. You have to think before you open your mouth, and that the reason a lot of people don't communicate clearly is that they haven't thought clearly about what it is they have to say before trying to communicate it to somebody else. They haven't prioritized the ideas. So I think the links are improving, but actually, and I think wherever the push comes from is good, but I think the push is sort of coming from the wrong direction. That there's a first step to make, and obviously we have to do everything at once. I don't think we should stop trying to communicate with industry while we cross that barrier. But the initial problem hasn't been solved. That communication is time consuming, and it's a skill, and you need to learn to communicate to others, to your peers first, respectfully and with dignity, and with evidence, but also listening. Academics are terrible at listening, and you need to do all of that before you launch yourself on the world. So yeah, we've got a long way to go, I think.
Do you have any science communication or psychon philosophies that you abide by to help encourage the communication between whether it be academics to academics or from yourself to the public?
I don't know about philosophies. I think listening is the first thing. People don't listen to other people. You may meet a member of the public who is vehemently opposed to genetically modified crops, or climate related mitigation strategies, whatever it is, and I think listening to why they think what they think before launching into why they're wrong is always helpful. But the basic philosophy is just be a decent human being. Be respectful and listen to people, and don't be overbearing, and stand up for the evidence, but don't wallop people over the head with it unless they've had so many opportunities to take it up and they're not, if they're willfully mixing up their ideology and their understanding of evidence, then you can probably hit them over the head with evidence a little bit. But it's basically be a decent human being. There's no difference in communicating. And so I'm sort of not necessarily a fan of media training courses. They used to have a place 10 years ago when the only time scientists ever came out of the lab was to talk to a newspaper journalist. I don't think they have a place now the way they're currently run, when there's Twitter and Facebook and social media, and basically everything starts with a conversation. And before you worry about having a conversation with Jeremy Paxman, how about you practice exactly those skills with your awkward neighbour who refuses to believe that science is worth funding, right? If you can have a respectful, dignified conversation with that neighbour, then if a journalist ever comes your way, you'll be fine. The problem is the first thing is the non-glamorous thing that no one wants to do, which is just, be a good person. It's hard and it's annoying, and other people are annoying quite frequently. And that's just part of being human, but you can listen and learn and move the debate forward constructively. And that's so it's not really a philosophy, but it's just, I get very frustrated with everyone trying to sort of glamorize everything, and it's very simple. It's about being a decent human being.
And just sharing stories, sharing experiences, and kind of just listening to the other person, understanding why they believe what they believe, for whatever reasons, and respectfully acknowledging that, and I suppose not necessarily throwing facts at them, but just working with it and just kind of saying, well, have you thought about looking into it from this perspective, or looking at it in this way, I suppose?
Yeah, and that's the way you move a debate forward constructively. And of course there are times when you need to have the very hard argument, but it's not most cases. And most people are interested. We start on this platform that most people think science is pretty cool, and they may think that they don't understand it, and we can help show that they actually do understand, or they can understand perhaps more than they thought, or perhaps that there are more subtleties than they thought. So we do start from a good position, and we have to not squander that position. There's a lot of debate at the moment about the public's opinion on experts, and generally it's not really what the public currently seem to, what gets their backs up is people being condescending, different from disagreeing with an expert. So, and maybe it's always going to be difficult to have nuanced debates in the public sphere, but it's not impossible, and we have to keep striving for that.
I saw a great, I suppose, meme or picture the other day. There was it was one guy saying, you don't think the electrician is pretentious for knowing more than you. You don't think the plumber is pretentious for knowing more about plumbing than you. Why do you think scientists are pretentious about knowing more about science than you? And it might just been a few bad eggs in history that kind of been condescending to others and kind of given this perception. But like you said, it is unnecessary.
Well, the other thing, I saw that cartoon too, and the other thing about that is that fundamentally the plumber arrives, and if they are any good, when they leave, something works. So there's a very sort of direct connection between now it might stop working a week later. They didn't do a good job, but there's a very direct connection between them knowing something and them doing something useful with it. And in science, that connection is much harder to make. You vaccinate a child. The evidence in favour of that being a good thing is held in statistics of many thousands of vaccinations, many thousands of medical tests, outcomes over decades. So it's very difficult to see the direct relationship quite a lot of the time. And obviously the world is complex. I mean, that's the difficulty of this, living in a very complicated world, is that we used to live in a situation where you could say A causes B causes C. Steam engine's brilliant. This bit pushes on that bit, and that turns that thing round, and the thing pushes on the thing, and then something drops out the other end. And science used to be like that, I think. And now we're really getting into the nitty-gritty of the sort of complicated everyday world, and it's not like that anymore. And so understanding the nuances of what is actually happening and representing that fairly is absolutely a challenge. It doesn't mean that you give up on it or that you dumb it down. It's just that you have to work a bit harder.
It kind of implies that you need to have some prior knowledge in this field to understand the next step, like the steam engine analogy you just used. But in the field of knowledge of science, whatever discipline it is, you need to know A to get to B to get to C, whereas most people who aren't in that profession might have just been educated in the basic concepts and the basic core stance, and then the rest of it comes on the reliance of trust that they have between scientists and the science. So the ones that communicate it, or the ones that are actually doing the research, they have to end up, unless they do all this research themselves, they have to kind of just trust what's being conveyed, I suppose.
But also, this is where the thinking clearly comes in, because you're presented with a whole load of facts, like most experts, and you could call them scientists, they might be economists, whoever it is, they know loads of stuff, but they don't prioritise it on a regular basis. And they don't think through to the core of actually what matters. They just go, oh, it all matters. And that's usually not true. There'll be an overriding concept, which is the big picture, and then you drill down to the other bits. And so if you have to think very, very clearly about what you're communicating to make sure that it's the big picture thing first, and then these other things are sort of nested underneath. And so thinking clearly is an important part of conveying the most helpful knowledge. It may well be nuanced, but you have to give people a chance. You have to show them the map before you tell them where they're going. But yeah, I think that's why clear thinking is really important. And it's hard, and most people either don't have the time or don't often see it done. That's the other thing. One of the things we've all had is we've seen terrible lecturers and terrible seminars given. And the problem is, at the end in academia, what happens is people stand up and say, oh, thank you, Professor so-and-so, for giving such an amazing lecture. And I'm usually sitting there going, that was awful. He should have, tomatoes thrown at him or her for that, because it was dreadful. But everyone goes, oh, well, it was wonderful, and thank you for giving such a wonderful lecture. And the audience didn't understand anything and leaves feeling that they must be just not clever enough. And we see bad examples as well. That's the other problem with academia. We see bad examples rewarded and pomposity rewarded, and that's just a bad habit,
Do you have any advice for those that want to develop their communication skills and want to be able to think clearly, to be able to convey whatever it is towards an audience of whatever their choosing is? Do you have any tricks, tips, anything like that you can suggest?
It's about starting with the small things. So there's no sort of great, magic pill. It's just taking every opportunity, every time you talk to someone about your science or whatever it is, say something, and afterwards kind of think about, well, you say that first thing and then the discussion carries on a bit. And did you realise later on that they didn't understand the first thing you said? And actually it was the third thing you said that should have come first. And so you never know what someone else has heard. It's not about what you say, it's about what they hear. And those are Those are two different things. But you don't know what they hear unless they repeat it back to you in some sense. So that's why hands-on science things, those open days and that kind of thing at universities and in industry are really good, because you actually get to have those conversations, and then you get to the end and you realize they didn't understand the thing you said first. So it's about situations like that. It's just experience on the ground of listening to what people didn't get and refining it that way. So it's that sort of thing.
So rather than just conveying facts and stuff, it's almost conveying a narrative, telling a story. So in the field of oceanography, I suppose you'd be like, a hurricane forms not because a hurricane forms. You start off with the warm water, and then you start off with the latitude, and then with the circulation, and you kind of build it up step by step, and making sure an individual would understand why warm water is important for X, Y, and Z, and then from that you'd be like, why are the currents important for the further steps?
Yes, a narrative is an interesting thing. It's both an enormous help and an enormous hindrance, because basically human brains are hardwired, however you phrase it, to pick up on stories, because it's been an extremely useful social tool. Stories are how humans have conveyed information. I mean, before there was ever an instruction manual, there were stories. If you look at the, cultures, for example, perhaps in the Pacific, where they are an ocean nation, they're boats, there's a lot of knowledge that goes into how to rig a boat and how to get from A to B and all that kind of thing. And the technical knowledge was wrapped up in stories. And also humans are gossiping. Soap operas are not this sort of, not necessarily something to be looked down on. They're almost a celebration of the human ability to retain stories and to create stories. So humans are really good with stories, but the problem is that when you've got a complex system of information, you may not be able to encapsulate it in a story, but the human brain will be looking for a story anyway. So this thing in science that you hear now, you've got to have a story when you convey your science, that's only because the human brain you're talking to is going to make up a story anyway. Because that's what human brains do. So you might as well make sure it's the one that you've sort of approved first, rather than one that they sort of, where they put the bits together for themselves and get the wrong end of the stick. So narrative's interesting. You have to use it to some extent, because that's how human brains work, but it's not necessarily the best way of conveying science.
It's really interesting on that story front, especially like you said, historically, our ancestors have always used stories to communicate. You're in Sydney right now, so in Australia, Aboriginals, or stories of Aboriginals, are still kept very well intact, a lot by the still native population. And there are some stories that I've heard, I think they called it rainbow serpent spirit or something like that, and it was a story about a cave down in Margaret River in Perth, or in Western Australia, and it was always about this ebb and flow of tide, and for certain seasons it would have no inflow at all, and that was just due to rainfall and the anthropogenic nodes and stuff like that. And they didn't obviously know that stuff at the time, but they would say that because it would be hollow, there would be a different wind that would come through. It would just be not dampened, I suppose. And they used to say that was a monster that lived in there, and then during the summer the serpent would come through, wash it away with the water and clear it out and take away the serpent. So that's, I suppose, an example of a story that it's got detail in it, but it's got a narrative to it, but the details, I suppose, are lost. They didn't know them at the time. But
those common. There's stories, especially around the coast, sea level having risen, and there are stories that are in, the Aboriginal oral histories of things that happened 6,000 or 7,000 years ago. And they describe islands being there, and they've looked and found that the islands were there 7,000 years ago, and that has been maintained in oral history as a way of conveying information. So oral history is very powerful for humans. It clearly works. It doesn't always work. You can always cherry pick cases where something happened to survive. You don't know that's true for every single case. However, it clearly can work. Sometimes it's very powerful thing. And scientists don't pay much attention to culture. That's another thing, is that traditionally that sort of thing was dismissed. Scientists would say, we have our Western methods and we know better. We measure things differently now and we know the right answer. And that a lot of traditional knowledge gets sort of steamrolled And I think, it's only we're just catching the tail end of it, this traditional knowledge which has built up over generations, and it's worth listening to.
So you're currently over in Australia for the Cosmic Shambles show, if I'm correct. Is that why you're in Sydney at the moment?
Yeah, so there are 5 of us that have come out from the UK, and the Cosmic Shambles is a concept that it's basically confusing until you've seen one, and then it makes perfect sense. Robin Ince, who was had the idea originally 10 or so years ago, just went, well, why should science be separate from everything else? Why not put science and comedy and music all in the same room? Because that's what humans are like, right? Just, no one assumes that because you're a musician, you're never going to laugh at a joke, or because you're a comedian, you're never going to find science interesting, or because you're a scientist, you're never going to pick up a violin. And so these shows are sort of a celebration of all the variety that comes along with human culture. And they're focused on science, but they're not all about science, and they're not bashing anything else. So these shows they're sort of hosted by Robin Ince and Josie Long. There's huge variety of guests. So there's 5 of us from the UK, and everybody else is local comedians and musicians and scientists. So it's a little bit of everything, and they're very varied. They're huge amounts of fun. Everyone learns something because everyone learns about everybody else's stuff, and they're fun and lively and human, and it's the human side of science, and why not celebrate it? So these shows are, and it's exciting for us because I've not met most of the guests that will be on in these shows. We've got Melbourne, so Sydney, and then Melbourne, and then Perth right at the end, and then in New Zealand, Christchurch and Auckland and Wellington. And I don't know most of the people that will be with us. I met Dr. Carl yesterday for the first time, and I was very embarrassed because I was sort of aware of him, but I hadn't realised quite how big a deal he was here. And then he said he knew me because of stuff I write in Focus magazine, and I felt very sheepish. Anyway, so we're meeting these great people who are here anyway in Australia and New Zealand, but they don't necessarily get put in the same room together. So the idea is to sort of introduce this concept and get the ball rolling here. So if anyone is nearby any of those cities, look at Cosmic Shambles. The description may well not make any sense to you, but come along anyway, and I promise you will love it.
I can tell you that the 13th of April is the Perth one. I'm looking at the site right now. And I also recently found out that you'll be joined by Renee Sayers over in Perth as someone I volunteer with at the moment, who coordinates the Fireballs in the Sky project and all these other good things. Like, she's a delight.
There are loads of brilliant people, and it's very, very varied. So it's all, and some of them, not all of them have been announced. That's the other thing. So it's not just the people who are on the list at the moment that you will see. There are surprise guests all the way along the way. So yes, it's always these shows. When we do these shows in the UK, Robin doesn't announce any of the guests. So you turn up not knowing anything about who's going to be there, and the surprise is half the fun. So here we had to release a few names to give the idea, but there's some extra sort of Easter eggs in there as well.
That's definitely one thing I miss about living in Australia compared to when I used to live in the UK is the diversity, or the spontaneity of the shows over here. They're definitely not as frequent, and it's not like you can just rock down to the BBC and turn up and buy a ticket to the next event that's there that night. It's a lot more sparse and organised over here, which is a shame.
Well, maybe this will be the start of a new wave, and everything will get a bit more spontaneous. That's the reason we're here, because somebody said we should, someone wanted to have this on your side of the planet. So we're just here as the seed, planting a seed that's hopefully going to grow.
That would be good to see. Thank you very much for joining me on the show. It's been a delight to have you.
You're very welcome. It's been fun to chat.
Do you have anything you'd like to add or advocate for before we finish?
I'm supposed to give my book a plug, right? Otherwise my book publicist will get upset. So Storm Teacup is about all those human little everyday things that absolutely demonstrate the laws of physics. And the lovely thing about it is that by playing with the everyday world of these little mundane things, you also, by learning those laws of the universe, you also learn, what's keeping our energy supplies going, how medical testing works, how the weather works, the same physics that is in these toys also explains the big important things that citizens need to know. So that's kind of my take on physics, and no one talks about it that way, so I did. But it's fun and interesting. So if anyone's interested in that kind of stuff, the book's called Storm in a Teacup, and it's out here now.
It's been given fantastic reviews, and it's actually in my to buy list for the past, I suppose, month before I knew I was going to speak to you. Otherwise, I probably would have read it before. But sorry about that.
No problem. Anyway, so that was the book club. There you go. Tick box on that.
Thank you very much for coming on the show. It's been great to have you.
And that was Helen Czerski. Thank you very much, everyone, for joining us. And I'd like to thank Helen again for coming on the show and giving us your time. It's truly appreciated. I will place links in the description of the show for her book, A Storm in a Teacup, and also tickets to Cosmic Shambles Live, the Australian tour. If you enjoyed the show, as I said before, please pop onto iTunes and subscribe, rate and review. It really does help. And also, I encourage you to check out Ace Podcast Network. There is a fantastic array of shows on there, and they're continuously growing every single week. If you'd like to get in touch with us or feature on a later episode, please contact us on vaguecomments@gmail.com or get in touch with us via submitting a form on our website, www.vaguelyaccurate.com. As always, I'll see you next week. Take care, guys.